Leah here from leahforsci.com/MCAT, and in this video, we're going to look at glycolysis, starting with phase 1, the investment phase. What is glycolysis? Glycolysis comes from the word glyco, which should remind you of glucose, and lysis, which means to break. Glycolysis is the reaction in which we take a 6-carbon glucose and break it into 2 3-carbon pyruvates plus energy. This is a universal metabolism pathway used not only in humans, but many other animals and even microorganisms. Glycolysis is a very involved reaction, and for the MCAT, you have to know the names, the structures, and the enzymes. And so I want to break this down, where in part 1 we're going to look at the investment phase, where we put energy in. Part 2 is the payout phase, where we now get some energy out. We'll summarize it all in part 3 from a logical rather than a technical perspective. Now, before you worry about copying down all of the structures, the names, and the enzymes, I've got you covered with a glycolysis cheat sheet, which you can find on my website along with the other videos, leahforsci.com/glycolysis, or see the link below. The first step in glycolysis is to trap a molecule of glucose in the cell, specifically the alpha-D glucose. As a reminder, humans can only utilize the alpha-D glucose because we are very bad at utilizing the beta. We are bad at utilizing beta, but ruminant animals like cows and goats and sheep, they have microorganisms that help them digest the energy found in grass, but we don't. In step 1, in order to trap the glucose in the cell, we add a negative phosphate group onto carbon 6. The product is a glucose 6-phosphate, or G6P. That phosphate group means that glucose can no longer get back out through the glut transporter, which is how it got into the cell, and that means it's now available to be attacked by additional enzymes undergoing additional reactions without escaping. Step 1 in glycolysis is a one-way reaction. This means that once glucose is phosphorylated, this cannot be reversed by the same enzyme, and that means the cell is committing to continuing on the glycolysis pathway. In order to complete this reaction, the phosphate group, which moving forward I'm just going to show as a P with a circle, comes from a molecule of ATP. ATP stands for adenosine triphosphate. It has 3 phosphate groups, and when we take off the phosphate, we're left with a DP, which is adenosine diphosphate. It's missing that 3rd phosphate that we put on glucose. ATP is the primary source of energy in a living system. It's the currency. It's how you pay for reactions. And so by utilizing ATP, this is an investment step. We're paying with a phosphate to start this reaction. And the enzyme that catalyzes this reaction is called hexokinase. I realize this is a lot to memorize, so when you're looking at the structures and especially at the enzymes, don't just memorize the name. Try to understand what the name means and why this specific enzyme name, hexokinase, connects to this reaction. The name hexokinase comes from hexo or hexose, which is a 6-carbon ose sugar. Anytime you see ACE, that tells you it's an enzyme, but kinase specifically is an enzyme that transfers a phosphate group. In this reaction from ATP onto carbon 6 of glucose. Most of the cells are going to use hexokinase, but the reaction is slightly different in the liver that uses glucokinase, and that has to do with why the liver is utilizing glucose, perhaps to store it, where the rest of the cells are utilizing glucose to burn it for energy. Another reason for adding phosphate onto glucose is to destabilize the glucose molecule. Glucose, unlike the other sugars, is very stable in a chair conformation because all of the OH groups are equatorial. Adding a negative phosphate introduces some instability into the molecule, which allows it to open up, which allows us to proceed to the next step. Step 2 is the reversible conversion from glucose 6-phosphate to fructose 6-phosphate, F6P. If you're wondering how we went from a 6-membered ring in glucose to a 5-membered ring in fructose, the answer is you can't. You can't simply pull a carbon out of the ring. Instead, we have to go from the chair or Haworth conformation to the open form, which we'll show in a Fisher projection before the reaction can proceed. You'll notice that even with the phosphate group, glucose still favors the cyclic form, but every time we form a glucose and it gets isomerized to fructose, Le Chatelier's principle dictates that another glucose will go from cyclic to linear form, so it can react and another, which is how we get all of the glucose to react. Let's take a look at what happened. Notice that everything from carbon 3 onward is exactly the same. The isomerism happened at the top of the molecule, where glucose had an aldehyde on carbon 1, and fructose has a ketone on carbon number 2. What happens in this reaction is the aldehyde on carbon number 1 is converted to an enol between carbons 1 and 2 through ketoenol tautomerization. That enol is then tautomerized again so that we get the ketone on carbon number 2. Once we have a fructose 6-phosphate, we're able to reform the cyclic structure, because remember, in the cell, they're always in equilibrium between linear, which we show in Fisher, and cyclic, which we show in Haworth. The enzyme that catalyzes this reaction is called a phosphoglucose isomerase. Phosphoglucose, because it acts on a phosphorylated glucose molecule, and isomerase, which ends in ase, telling us that it's an enzyme that creates an isomer. In this case, we have a constitutional isomer, because if you count the atoms, nothing has changed between carbons 1 and 2, except that we've moved some atoms and bonds around. Notice that we lost 2 hydrogens on carbon number 2 to form the ketone, but we gained 2 hydrogens on carbon 1 when we lost the aldehyde. Think of steps 1 and 2 as the warm-up in glycolysis. The cell knows it wants energy, it knows it wants to proceed, but up till step 2, it can still change its mind. Step 3 is considered the rate-limiting step of glycolysis because when the cell goes through step 3, it is committed to seeing this all the way through. Why is step 3 a rate limiter? In step 3, we're taking a molecule that already has a lot of energy invested, and we're putting even more energy in because we know we're going to get energy out later. How? We take fructose 6-phosphate and add a phosphate group from another ATP molecule in a one-way reaction that gives us fructose 1,6-bisphosphate, or F16BP. That's a fructose molecule with bisphosphate, 2 phosphate groups, 1 each on carbon 1 and carbon 6. ATP, adenosine triphosphate, having given up the phosphate, is now left with only 2 for ADP, adenosine diphosphate. The enzyme that catalyzes this reaction is called phosphofructokinase, or PFK, and is considered the most important enzyme in glycolysis. Phosphofructokinase comes from phosphofructo, a phosphate group on fructo, and kinase, as you remember, is an enzyme that catalyzes the addition of a phosphate group, in this case a second phosphate group, onto the fructose molecule. Don't forget that the cyclic structure is in equilibrium with the open or linear form that I drew here in Fisher projection. I want you to pay attention to what we have on this molecule. I want you to see how even though the molecule isn't exactly symmetrical, if we break it down the middle, we have about the same number of atoms or groups. We have the same number of oxygens and the same number of phosphates on both sides. This is critical for the next step because now that we've invested all the energy, now that we have the phosphate groups here, we want to get one step closer to 2 pyruvates, which means we have to find a way to break the molecule. To break the molecule, I put the 2 halves in different colors so that we can follow their progress towards pyruvate. In step 4, fructose 1,6-bisphosphate, shown here in 2 different colors, will get broken right here. to give us dihydroxyacetone phosphate, DHAP, and glyceraldehyde 3-phosphate, G3P, also sometimes called GAP. If the names are confusing, take a look at what we have. Remember that to add the phosphate group, we needed an OH, so the dihydroxy refers to the OH that would have been there, and this OH as 2 OHs. Acetone, because this right here is a 3-carbon ketone or acetone with a phosphate on the OH. Glyceraldehyde 3-phosphate comes from a glycerol molecule, which would have been a 3-carbon chain with 3 alcohols, but in this case, it's a glycerol aldehyde with an aldehyde on carbon 1 instead of one of the 3 OHs. 3-phosphate, because that is on carbon number 3. Now here's the problem with step 4. Pyruvate, our ultimate goal, is one molecule. In order to get to pyruvate, we need glyceraldehyde 3-phosphate, but when we broke this molecule in half, every glucose gave us one good G3P and one unusable DHAP, dihydroxyacetone phosphate. Given how important glucose is to the cell, we can't simply take the one and toss the other. That would be a tremendous waste. That means half of the energy that you're eating, half of your glucose consumption would be wasted. And that is why in step 5, we have to find a way to rescue all the DHAP. But first, the enzyme that catalyzes this reaction is called an aldolase. Aldolase tells us we have an enzyme that catalyzes an aldol reaction. Aldol reaction? Wait a minute. Isn't that the reaction you learned in organic chemistry, where you take 2 aldehydes and fuse them together to form a molecule that has both an aldehyde and an alcohol for an aldol condensation? Actually, yes, but in reverse. If you look at these 2 molecules, we have an aldehyde that can react with this molecule, the ketone, it can be an aldehyde or a ketone, to give us an aldol, which we have in fructose 1,6-bisphosphate, but that's the reverse reaction. Anytime you have a reversible reaction, the enzyme name can come from the forward reaction or, as you saw here, from the reverse reaction. In step 5, we're going to rescue the dihydroxyacetone phosphate. This is not in a form that we need, so we want to find a way to convert the dihydroxyacetone phosphate to glyceraldehyde 3-phosphate, and that will be catalyzed by an enzyme called the triose phosphate isomerase, or TPI. From the name, we see that we have triose, a 3-carbon sugar, DHAP is a 3-carbon sugar, phosphate isomerase. We're isomerizing or moving the phosphate group. But first, what is the difference between DHAP and G3P? Carbon number 3 has a phosphate group that doesn't change. Carbon number 2 has to convert from a carbonyl to an alcohol, and carbon 1 has to convert from an alcohol to a carbonyl. This should once again remind you of that double keto-enol tautomerization. Carbon number 2, instead of a carbonyl, gets C single bound OH for the alcohol, plus another H, and carbon number 1 is going to lose 1 hydrogen here, 1 hydrogen here, leaving it with just 1 hydrogen, and the oxygen now gets a second bond to form the aldehyde. This is just another way of drawing glyceraldehyde 3-phosphate, where carbon 1 is the aldehyde, 2 is an OH, and 3 has a phosphate. Interesting note about TPI. This is considered one of the few perfect enzymes in a biological system because it's very efficient and has a very high turnover rate, which, if you think about it, is really important given that half of every single glucose molecule is not usable until TPI turns it into G3P so that we can get the maximum energy out of every half of glucose. Now that we have 2 glyceraldehyde 3-phosphates, one from the initial G3P that formed when we broke fructose 1,6-bisphosphate, and the second from converting this unusable half DHAP into G3P, So far, we invested. We spent money in the form of ATP. We put in all that effort into taking glucose, changing it, breaking it, fixing the broken halves. And now that we have the 2 glyceraldehyde 3-phosphates, we're ready to go on to phase 2, the payout phase, where we start collecting and taking energy out of glycolysis. And that is exactly what we're going to discuss in the next video. But first, make sure you give this video a thumbs up, subscribe to my channel, and hit that bell icon so you don't miss out on any new videos. Then visit my website for the next video along with the glycolysis cheat sheet, which you can find linked below, or go to layerfortsci.com/glycolysis. Again, that's layerfortsci.com/glycolysis.